So first Cauchy's integral theorem prove చేసే ముందు Green's theorem. Already Green's theorem మీద మన ప్రాబ్లమ్స్ ఫస్ట్ ఇయర్ లో Green's theorem మీద ప్రాబ్లమ్స్ అండ్ స్టేట్మెంట్ కూడా మనం ఆల్రెడీ డిస్కస్ చేస్తుంటాము. సో ఈ స్టేట్మెంట్ ని మనం ఈ Cauchy's integral theorem లో యూజ్ చేస్తుంటాం అమ్మా. సో స్టేట్మెంట్ ఈస్ if m of x comma y n of x comma y. So mn two variables mn are two functions in two variables x and y are continuous functions of x and y and having partial derivatives dou m by dou y and dou n by dou x in a region capital R of xy plane bounded by a simple closed curve C, then the statement of Green's theorem is integral m dx plus n dy equal to double integral dou n by dou x minus dou m by dou y dx dy. So this is a Cauchy's integral theorem statement. మనం ప్రూవ్ చేసే ముందు గ్రీన్స్ థియరం యొక్క స్టేట్మెంట్ ని డిస్కస్ చేసుకున్నాము. Next theorem is Cauchy's theorem. So this is also known as Cauchy's integral theorem. The statement is if a function f of z is analytic and f dash of z is continuous at each point inside and a closed curve C, then integral over C f of z dz equal to 0. Proof of the theorem is, in the statement we have to given f of z is analytic function. That means Cauchy-Riemann equations are satisfied. So Cauchy-Riemann equations are dou u by dou x equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. So these are CR equations. Now consider integral over C f of z dz. Let z is x plus iy and dz equal to dx plus I dy and analytic function f of z equal to u plus iv. Now to evaluate integral over C f of z dz equal to integral f of z is u plus iv and dz is dx plus I dy. So that equal to integral u dx plus I into u dy plus I dx minus v dy, that equal to, then separate the real part and imaginary part. We have integral u dx minus v dy plus I into integral u dy plus v into dx, that equal to say equation 1. Already given that f of z is analytic function. So by CR equations the partial derivatives of u and v, that is dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y are continuous. So by using Green's theorem statement, we know that integral m dx plus n dy equal to double integral dou n by dou x minus dou m by dou y dx dy. So this is the statement of Green's theorem. We have to apply this Green's formula in equation 1. We get integral C f of z dz equal to, so first term is in equation 1 u dx minus v dy. So this is in the form of integral m dx plus n dy. Here m is u and n equal to minus term, that equal to double integral minus dou v by dou x. So this is dou n by dou x minus dou m by dou y is dou u by dou y dx dy plus I into double integral u dy plus v dx. Here m is v and n is u. So by using Green's theorem, I double integral dou n by dou x is dou u by dou x minus dou m by dou y is dou v by dou y of dx dy. that equal to double integral dou u by dou y minus, by using CR equations, dou v by dou x is minus dou u by dou y. So that equal to the above integral change into double integral dou u by dou y minus dou u by dou y dx dy plus I double integral. Here also substitute CR equations, dou u by dou x minus dou u by dou x dx dy, that equal to first integration is 0 plus I into second integration is also 0. So that equal to integral over C f of z dz equal to 0. Next, the statement of extension of Cauchy's theorem for multi-connected regions. So, if f of z is analytic in the region R between two simple closed curves C1 and C2, then integral C1 f of z dz equal to integral C2 f of z dz. So, this theorem proof is not necessary. Next theorem is Cauchy's integral formula. So the statement of Cauchy's integral formula is, if f of z is analytic within and on a closed curve C, and if small a is any point within C, then f of a equal to 1 by 2 pi I integral over C f of z by z minus a dz. Proof of this theorem. Uh, in this statement, given that f of z is analytic function, then f of z by z minus a is analytic at all points except z equal to a. So given function is f of z by z minus a. Now the function f of z by z minus a is analytic between the curves C and C1. These two curves are we have to taken. We have to use the statement of extension of Cauchy's theorem. Integral over C f of z by z minus a dz equal to integral over C1 f of z by z minus a dz. So, for any point on C1, let z minus a equal to r into e power I theta. So, in this function, we have to change into polar coordinates. Then, z equal to r e power I theta plus a and dz equal to r into e power I theta. So then multiple of I into d theta. So this is the differentiation with respect to z. Then we have to take in theta limits are 0 to 2 pi. Then the integration, it may be changed into integral 0 to 2 pi f of z means r e power I theta plus a by z minus a equal to r e power I theta, and dz is r e power I theta into I into d theta. So integral over C f of z by z minus a dz equal to, then I is a constant, we have to write without integral, I integral 0 to 2 pi f of a plus r into e power I theta d theta. That is equation 2. So see in this figure, let the circle C shrinks to the point A. So shrinks means to make something smaller to the point A, then r tends to 0. So equation 2 becomes, then substitute r equal to 0 in equation 2. Integral over C f of z by z minus a dz equal to I integral 0 to 2 pi f of a plus, so r is 0 into d theta. So I into f of a is a constant function, integral 0 to 2 pi d theta. So d theta integration is theta with the limit 0 to 2 pi. So finally we get 2 pi I f of a, which implies f of a equal to 1 by 2 pi I integral over C f of z by z minus a dz. So this is the statement of Cauchy's integral formula. Next theorem is converse of Cauchy's theorem. So this is also known as moveras theorem. So statement is, if f of z is continuous in a region R and integral over C f of z dz is 0 around a simple closed curve C, then f of z is analytic in region R. In this statement, we have to given integral over C f of z dz equal to 0. Now we have to prove that f of z is analytic. So f of z is analytic means we have to prove that it satisfies Cauchy-Riemann equations. Let the line integral of f of z we have to taken from fixed point z0 to a variable point z and given integral over C f of z dz equal to 0. Then we have to apply the limits, upper limit and lower limit, integral and small f of z equal to u plus iv. Some of the difference, let capital F of z equal to capital U plus I capital V. So f of z equal to u plus iv equal to integral z0 to z f of z dz. Then capital U plus I capital V equal to integral. Already we know that f of z is small u plus I small v and dz is dx plus I dy. Here capital U plus I capital V equal to integral. So multiply with u plus iv and dx plus I dy. We get u dx minus v dy. This is real part plus I integral v dx plus u dy. This is imaginary part. Then comparing both sides real and imaginary parts. Then u equal to capital U equal to integral u dx minus v dy, capital V equal to integral v dx plus u dy. So differentiate under integral sign. So first one is capital U equal to integral u small u dx minus v dy. So differentiate with respect to x, we get dou u, dou capital U by dou x equal to small u, dou capital V by dou x equal to small v, and dou u by dou y equal to minus v, dou v by dou y equal to u. Now we have to verify dou u by dou x is u, dou v by dou y equal to u. Therefore, dou u by dou x equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. Therefore, CR equations are satisfied of u and v. Therefore, f of z equal to u plus iv is analytic. So, f of z is capital U plus I capital V. Now, we have to prove that f of z equal to small u plus I into small v is analytic. So, f dash of z equal to dou u. U is capital U, dou u by dou x plus I into dou v by dou x. That equal to dou u by dou x is already we know that small u plus I into small v. Therefore, capital F dash of z equal to small f of z. Therefore, f of z is analytic. Already we know that the derivative of f of z is also analytic. Therefore, small f of z is analytic. Problems on Cauchy's integral theorem. First problem is evaluate integral e power 2z by z minus 1 into z minus 2 dz where C is the circle mod z equal to 3. Solution is to evaluate integral e power 2z by z minus 1 into z minus 2 dz for the circle C is mod z equal to 3. So, in this problem, important point is the difference between two theorems. Two theorems means Cauchy's integral theorem and Cauchy's integral formula is Cauchy's integral theorem statement is f of z is analytic inside the circle C. Then integral over C f of z dz value is 0. And f of z, this is the Cauchy's integral formula statement is f of z is analytic within and on a closed curve C is integral f of z by z minus a dz equal to 2 pi I into f of a. So this is the difference between two theorem statements. So first, to solve the singularities. Singularities means given in the given function, the denominator value is equal to 0. So the denominator value is z minus 1 and z minus 2 equal to 0. Therefore z equal to 1 and z equal to 2. So this is the two singularities in this problem. And also given circle is mod z equal to 3. So mod z, z means x plus iy. Mod x plus iy is root of x square plus y square. This is the magnitude formula, equal to 3. Squaring on both sides, x square plus y square equal to 9. So we have two singular points. First one is z equal to 1 and second one is z equal to 2. So first z equal to 2. This point is inside or outside. We have to verify inside or outside. So z equal to 2. Z means x plus iy equal to 2. So comparing both sides, real and imaginary parts. Real part is x equal to 2 and imaginary part y is 0. So then substitute in the circle equation x square plus y square equal to 9. We get 4 less than 9. Next singular point, z equal to 1. Z means x plus iy equal to 1. Here real part x equal to 1, imaginary part y equal to 0, and substitute in circle equation x square plus y square equal to 9. We get 1 less than 9. In this formula, two singularities are within and on a closed curve C. So we have to use the formula integral over C f of z by z minus a dz equal to 2 pi I f of a. So given problem is integral e power 2z by z minus 1 into z minus 2 dz. We know the formula is only integral f of z by z minus a dz. So the given integration, it may be changed into, we have to using partial fraction. Then we split this integral value in the form of integral f of z by z minus a dz. So we have to using partial fraction 1 by z minus a into z minus 2, or we have to using by observation method. Then split the 1 by z minus 1 into z minus 2. We get integral e power 2z into 1 by z minus 2 minus 1 by z minus 1 dz. Then the integration split into two integrals. First integral is integral e power 2z by z minus 2 dz minus integral e power 2z by z minus 1 into dz. In two integrals, here f of z is e power 2z. Now we have to use the integral Cauchy's integral formula. Integral f of z by z minus a dz equal to 2 pi I f of a. Here in first integral a is 2, in second integral a is 1. That equal to 2 pi I into f of 2 minus 2 pi I into f of 1. Here f of z equal to e power 2z. Therefore, integral e power 2z by z minus 1 into z minus 2 dz equal to 2 pi I. F of 2 is e power 4 minus 2 pi I. F of 1 is e square. Next problem is evaluate integral over c z plus 4 by z square plus 2z plus 5 dz, where c is the circle. Number 1, mod z equal to 1. Number 2, mod z plus 1 minus I equal to 2. Number 3, z plus 1 plus I equal to 2. Solution is to evaluate integral z plus 4 by z square plus 2z plus 5 dz. First, to find singularities. For singularities, let z square plus 2z plus 5 equal to 0. Then this equation can be changed into plus 5. Plus 5 means 1 plus 4. So that is z plus 1 whole square plus 4 equal to 0. Z plus 1 whole square plus 2 square. So this is 2 square means minus 2 square I square equal to 0. This is a square minus b square. So a plus this equation can be written in the a plus b into a minus b. That is z equal to -1 minus 2y and z equal to -1 plus 2y. These are two singularities of z square plus 2z plus 5 equal to 0. First, to find the given circle mod z equal to 1. Mod z means mod x plus iy equal to 1. Apply magnitude formula. We have root of x square plus y square equal to 1, which implies x square plus y square equal to 1. So, first singularity is z equal to -1 minus 2y. Z is x plus iy equal to -1 minus 2y. Comparing real and imaginary parts, x equal to -1, y equal to -2. Then these values substitute in circle equation x square plus y square equal to 1. We have 5 greater than 1. So 5 greater than 1 means it is inside the circle. Inside the circle means we have to use Cauchy's integral theorem. Integral f of z dz is 0. So, second singularity is z equal to -1 plus 2y. Z means x plus iy equal to -1 plus 2y. Comparing real and imaginary parts, x equal to -1, y equal to 2, and substitute in the circle 5 greater than 1. So, this singularity is also inside the circle. So, integral f of z dz equal to 0. Therefore, integral f of z means z plus 4 by z square plus 2z plus 5 dz equal to 0. So, second circle is mod z plus 1 minus I equal to 2. Z is x plus iy plus 1 minus I equal to 2. So, real part is x plus 1 plus I into imaginary part y minus 1 equal to 2. Using magnitude formula, root of x plus 1 whole square plus y minus 1 whole square equal to 2. Squaring on both sides, x plus 1 whole square plus y minus 1 whole square equal to 4. So, two singularities. So, first singularity is z equal to -1 minus 2y. To verify the singularity is inside or outside. So, here comparing real and imaginary parts, x is -1 and y equal to -2. Substitute these values in circle equation. So, -1 plus 1 whole square plus y is -2 minus 1 whole square, that is 9 greater than 4. And second singularity is z equal to -1 plus 2y. So, comparing x is -1 and y equal to 2 and also substitute in circle equation, we get 1 less than 4. So, this is the within the circle, and that means inside the circle. Therefore, given equation is integral z plus 4 by z square plus 2z plus 5 dz, that equal to integral z plus 4 by, already we find the singularities, z square plus 2z plus 5 is z minus of -1 plus 2y into z minus of -1 minus 2y into dz. So that equal to integral. Now we have to write without the, in the singularity, without the value is 9 greater than 4. So this is the singularity z equal to -1 minus 2y. So this is without the integral value. Now we have to write integral z plus 4 by z minus of -1 minus 2y. Singularity is without the circle. That's why this integration, it can be written as the denominator value will be taken in the numerator. So this is the outside of the circle. So integral z plus 4 by z minus of -1 minus 2y by, so z minus of -1 plus 2y. So this is the within the circle into dz. So that equal to, in this integration is in the form of integral f of z by z minus a. Here f of z equal to z plus 4 by z minus of -1 minus 2y and a is -1 plus 2y. By using the Cauchy's integral formula, that is 2 pi I into f of a. 2 pi I into f of a. A means -1 plus 2i. Already write down f of z is z plus 4 by z minus of minus 1 minus 2i. Then substitute a equal to minus 1 plus 2i. So finally we get 2i plus 3 by 4i, that equal to I into 2 plus 3i by minus 4. Then substitute f of a. Finally we get pi into 2i plus 3 by 2. Next, given circle is mod z plus 1 plus I equal to 2. Mod z means x plus iy plus 1 plus I equal to 2. Then its magnitude root of x plus 1 whole square plus y plus 1 whole square equal to 2. The squaring on both sides, we get x plus 1 whole square plus y plus 1 whole square equal to 4. So first singularity is z equal to minus 1 minus 2y. Comparing real and imaginary, we get x equal to minus 1, y equal to minus 2. Substitute in the circle, we get 1 less than 4. Next singularity is z equal to minus 1 plus 2y. So here x equal to minus 1 and y equal to 2. Substitute in circle equation, we get 9 greater than 4. So in this circle equation, z plus 1 plus I equal to 2. The singularity z equal to minus 1 plus 2i is outside the circle. Z equal to minus 1 minus 2i is inside the circle. Therefore, integral z plus 4 by z square plus 2z plus 5 dz equal to integral z plus 4 by, we have to write then z square plus 2z plus 5 in two singularities, z minus of minus 1 plus 2y into z minus of minus 1 minus 2y dz, that equal to, now we have to write in this function f of z in two singularities. First singularity is within the circle and second singularity is without the circle. Now we have to write the function integral z plus 4 by z minus of minus 1 plus 2y is without the circle by z minus of minus 1 minus 2y. So this singularity is within the circle. That's why we have to write the function in this form, that equal to, so this is in the form of integral f of z by z minus a. Here f of z is z plus 4 by z minus of minus 1 plus 2y and a is minus 1 minus 2y, that equal to, by using Cauchy's integral formula, 2 pi I into f of a. Here a is minus 1 minus 2y, that equal to 2 pi I into, then substitute a value in the function f of z, we get I into minus 2y plus 3 by 4, that equal to minus pi into minus 2y plus 3 by 2, that is pi into 2y minus 3 by 2. So this is the calculation of f of a value. Let f of z is z plus 4 by z minus of minus 1 plus 2y. Then substitute a is minus 1 minus 2y in the function f of z. We get minus 2y plus 3 into I by 4.